leads into one of the things I want to talk about next. So JC said that the 6 protons in the center of a carbon atom, say it's a carbon atom, okay? So what about the neutrons? Well, we had 6 neutrons in the last carbon atom, but do all carbon atoms have 6 neutrons? The answer is no. There are different isotopic forms of carbon. Do all carbon forms, isotopic forms of carbon have to have 6 protons in their nucleus? Yes, okay? So all an isotope is basically atoms of the same element, same number of protons, but they differ in the number of neutrons. That's it. That is totally it. And it's not random, like, how do I say this? Like, there are certain combinations of protons and neutrons and electrons that are stable. And so Mother Nature, of course, has settled upon only stable forms of elements. Sometimes I say neutrons are kind of like the salt and pepper, and Mother Nature puts a few more, a few less. Oh, sorry, there's still more, sorry. So, in a minute, when we pick on carbon, there's going to be a carbon with a mass number of 12. That's the most common form of carbon. And then there's one with a mass number of 13. So there's a carbon 12 and a carbon 13. Do they both have 6 protons? Yes. Do they have different numbers of neutrons? Yes. So just for kicks, this is our carbon 12. This is our carbon 13. Which one has more which one has more neutrons? What's that? The 13, yep. This one has, instead of 6, it has 7 neutrons. And this has 6 neutrons. That's just how this works. But they both have 6 protons. And not so coincidentally, if you add 6 plus 7, you get 13. If you add 6 plus 6, you get 12. Okay. So this is, have you ever heard of the term oxymoronic phrase? Like it's like a phrase that just doesn't make sense. So to me, a single isotopic form doesn't make sense because isotopes means multiple forms and one isotopic form seems kind of dumb to me. So these actually, all of these elements, just going to kind of throw some at you. You don't have to memorize these by any means, but these you recognize as elements. And these atoms only exist in one isotopic form. You don't have to memorize this either. But this set in red of elements has 2 isotopic forms, and this has 3 or more isotopic forms. Now these are these little fact sheets that you can pick up at bookstores. Heck, you can pick them up at gas stations. I don't know how that works like that. But in here, for this one, if you look up here, that's actually elements. I'll pass that around. And it says the different isotopic forms of the elements.
Their percentages.
And their percentages, exactly. And this one's right here. So I'll have you kind of pass that around. We'll go like that. So, yeah, those little fact sheets are kind of fun. Sometimes you're like, hey, I think I should have one of those for my test. So like Jeremy said, not only do they say a carbon 12 and a carbon 13, but they say in nature how, what we say, abundant they are, what their percentages are. Okay. So just like with the carbon, I did carbon 12 and carbon 13. All we got to do to say which isotope we have is to say the mass number, which is the number of protons, which is set in stone, which is plus the number of neutrons, plus U, which can vary. Okay? So one of the things I want to emphasize is both a carbon 12 and a carbon 13 atom would behave chemically the same, but you could detect a difference in their mass. Okay, so here we go. Carbon 12. Notice this, and actually we're going to kind of talk more about this kind of designation. The symbol for carbon is C, and what we do is we put the mass number in the upper left-hand corner. Okay. This is a little different, where not only do we have the mass number in the upper left-hand corner, but also we have the atomic number, 6. The last one is kind of a little redundant, Because if you know it's carbon, then you know its atomic number is 6 from any decent periodic table. Okay, so you guys are going to have some homework doing this. Okay, and on the test you'll have some kind of chances at kind of mulling this over. So what we just saw, that convention, carbon 12 and 6, it looks like this. Where, remember we talked on Wednesday, we use an A for the mass number and a Z for the atomic number, which totally drives me nuts, but I do think it's German. So this is the type of question that you might have with this sort of concept. So here F stands for what element? Fluorine, exactly. The other day it was yesterday, I put FL. Like, ah. So fluorine. So do you guys have these answers? We'll go around the room again. And we'll start over here with Logan. Okay, Logan, what's the atomic number?
Of what?
Of this, fluorine.
Atomic number is 9.
It is 9. Very good. Ding, ding, ding. Perfect. Jared, what is the mass number?
19.
Perfect. 19. Alicia, how many protons does it have?
9.
It does have 9. Very good. And Tyler, how many electrons does it have?
Do you want this one? No. I think it's
Is it 10?
It's not 10. How did you get 10?
No, from the 9. The last, that was not talking.
Oh, I'll take those things.
That's what I said.
Well,
She's asking about
how many electrons does it have? So here's your hint or whatever. It has 9 protons, and if it's going to be neutral, how many electrons does it need to have? Yeah, it has to have 9. I think you're fine with that, Tyler. It has to have 9 electrons. And I don't know if this is what you were after, but so we're on now up to Becky. Becky, how many neutrons would it have then?
10.
10. And how'd you get that?
19 minus 9.
19, which is the mass number, which is protons plus neutrons, minus 9, which is the protons, equals 10. Yeah. Very good. So let's see, how do I want to say this? Now, back to Tyler, who said it has 9 electrons. Now, if it was charged, and we'll be talking about charged things, if it was charged, there would have been a symbol up there, a plus or minus, and a number, and so it's not charged.
So if it was off by 2, like 10 and 12, would it be a positive charge or a negative charge?
Depends on if the protons are more than the neutrons, then it's a plus. If the neutrons are more,
I think you mean
negative.
electrons. Because it's protons and electrons that make the charge difference,
Yeah, that's what I meant. If the protons are higher, then it's positive.
Yeah,
How
yeah.
many more? That's how I always.
Can't remember on the
count
next slide.
How many there are.
No, I don't. But we'll get to that. In fact, if we want to if we kind of want to look ahead a little bit, some of you guys maybe already know fluorine on the periodic table. Which group is it in? We did talk about groups in here, didn't we?
It's in halogens.
It is in the halogens, and all of the halogens actually pick up an electron. So was this what you were saying, Becky? If you see fluorine with anything other than neutral, it's actually going to look like this. F with a -1, okay? And then it could still be the same mass number and, of course, the same atomic number, okay? And in this case, this is kind of what JC was saying. If you see that it is negatively charged, that means it actually has an extra electron. So in that case, how many electrons would it have? 10, exactly. 9 plus 1, or 10 electrons. So that's kind of how that goes. And we'll be getting to that. So in the meantime, we're just talking about 2 isotopic forms of boron here. It's kind of, I like the whole Christmas thing going on in the nucleus of the atom. We have boron 10 and boron 11. Of course, boron 11 has just 1 more neutron in it. That's being shown there. So here's an assignment that will be due on Monday. We'll kind of take a look at this. And this is what these look like. How many neutrons are in each atomic, see, these are atoms. With given these atomic numbers, how many neutrons are there and how many neutrons are there? Okay, so my hint there is we can subtract, can't we, to get neutrons. Okay, very good. Now for the next one, it says, basically wants you to write the symbol for the element. So what's the symbol for iodine? I, exactly. So the symbol for the element, a dash, and then you're supposed to put the mass number. But in these cases, they don't give you the mass number straight up. They give you the number of neutrons. So for instance, let's pick on iodine. How many protons are there in an iodine atom? 53. I'll take your word for it. Use the periodic table, and it's the whole number there. Very good. So take 74 plus 53, and that will be what follows the dash. All right. And then the last one, we're supposed to use that shorthand where you have the symbol for the element. You have two things on the left. The top number is the bigger number. It's the mass number. And the bottom number is the atomic number. So, and each one of these, all they do is give the mass number. So you're supposed to take that number to the right and basically put it in the upper left, and then put the atomic number of protons in the lower left.
So we don't have to do the charge.
No, these are all, we're not talking about charged anything yet.
Okay.
We're getting there. Yeah. So, very good. Okay. So I do want to cover that last concept. We aren't going to go on to the next part. So one more homework assignment coming up. But there's another important thing about elements, and that's how much they weigh. Okay? So how much does an atom of a given type of element weigh? And I brought this up because you're like, well, if we pick on carbon, you know, all we got to do, we said it has carbon-12 has 6 protons, 6 neutrons, and 6 electrons. All we got to do is take these AMUs, multiply each of them by 6 and add them together, right? To get, and this is the cool thing, and I don't usually go into this very much, and I'm not going to. But a cool thing is that if you do that, you're going to get a little more mass than really a carbon atom has. So a little bit of the mass of those, the sum of those, 18 particles, a little bit of that mass is converting to what we call binding energy. It's called mass defect. But we don't have to worry about that because the periodic table, did I bring one today? Like the one that you're going to have on for your unit exam. Remember, this is exactly what you'll have in your unit exam. Okay? So the periodic table for carbon says 12.01. That means that a carbon atom weighs, on average, taking into consideration all the different isotopic forms of carbon, how abundant they are, 12.01 atomic mass units, or AMUs. That's it. So to make sure we're kind of still on the same page, remember I told you the other day that, and maybe TRO uses AMUs for atomic mass units, but these days scientists are just gone to the letter U, the symbol U, not mu, but U for atomic mass units. So, or U. All right. But the problem is carbon has a couple different versions. And as I pass this around, let's see, yeah, carbon has a couple different versions. Now, the carbon-12 version is 98.9% of all of the carbon atoms. The carbon-13, the heavier version, is 1.1%. So you really can't just add them together and divide by 2 to come up with this decimal number. Okay? That wouldn't work, because you have a whole bunch more carbon-12 than you do carbon-13. So there's a way to get to this decimal number we're going to talk about. So anytime you introduce a new mass unit, like atomic mass units, you have to have a standard that it was developed on. And so AMUs, atomic mass units, actually was developed around the element carbon, and it picked on the special form of carbon we've been talking about, carbon-12. So these might come in handy. I'm not sure. I usually tell you memorize this, but I'm not sure you necessarily need to memorize this. So AMUs, we're not used to dealing with AMUs. It's a mass. We don't do that. We don't have a balance that reads AMUs, but we do have a balance in the lab that reads grams. Okay? So 1 AMU is approximately equal to 1.661 times 10 to the negative 24th grams. Okay. Now that one I haven't committed to memory. The next one, and some of you who've kind of dabbled in chemistry are familiar with Avogadro's number. Okay. The next one, what's that?
Sounds like a food.
It sounds like a food. The next one I probably could come up with as being memorized. So if we take the inverse of 1.661 times 10 to the minus 24th, you'll get actually 6.022 times 10 to the 23rd. So 1 gram is approximately equal to 6.022 times 10 to the 23rd atomic mass units. And this is Avogadro's, does sound like a food. I'll spell it out. Avogadro's number. That is Avogadro's number. And that's not just a coincidence that it works out that way. Okay. So, by the way, the thing I'm going to show you how they come up with that decimal number, the average atomic weight for the atoms, this process we're going to go through in lab on Thursday. So in order to come up with a decimal number, we need to know relative percent. So I told you a minute ago, carbon, oh my gosh, carbon's got 98.9% of carbon-12, 1.1% of carbon-13. Those are the percent abundances, okay? So what those percent abundances mean, it's not by weight, it's by picking the number of atoms out. So anytime we talk about percents, they're parts per 100. But how do you get to a percent? It's kind of like, this is kind of like what you did with your egg. Basically, you have the total number of atoms, of all carbon atoms, and then you pick out in piles carbon-12, carbon-13, and then you put that number in the top. So this is the number of carbon-12 or carbon-13 atoms there are in a given number of samples. So the whole sample goes in the bottom. Okay, so that's how they come up with those. And I do think they're probably revisiting them and, part of the problem is to get like a representative sample, I think. So anyway, that's those percents that you see. So instead of carbon, if we pick on, what's Cu stand for? What's up there? What does Cu stand for? Copper. If we pick on copper, okay, it has two different isotopic forms. We have a mass number 63 and a mass number 65. So the upper left-hand corner is the mass numbers, okay? And if you were to go out and just get a representative sample from Earth of copper atoms, 69.09% of those copper atoms would be the lighter form, the copper 63, and 30.91% would be the heavier isotopic form. So just what that means, if you scale that up, not having 100, but if you go ahead and not have 1,000, but if you have 10,000 copper atoms, we kind of move the decimal over, what that means in 10,000 copper atoms, 6,909 of them would be copper 63, 3,091 of them would be copper 65. So it's kind of saying what those mean. But now we need a decimal number for carbon. So you see right away we really just can't, since they're not equal, if we had 50%, 50%, we could add how much one of them weighs and divide by 2. But we got more the copper 63 than we do of the copper 65. So we have to take that into consideration. Picking on neon now. We'll kind of see another chart kind of like this. If you read it from left to right, over here from left we have the three different isotopic forms of neon. You can kind of see neon 20, neon 21, neon 22 with their mass numbers. Of course, the 10 means the number of protons, which is the same for each. Over here, then, we have how abundant they are. So, again, we have a lot more of neon 20 than we do of the 21 or the 22. So the decimal number for neon is going to have to take that into consideration. Here are some other elements. Hydrogen's kind of cool. When I pass this around, you only saw 2 forms of hydrogen. There's normal hydrogen, and hydrogen for some reason is so important that the isotopic form of hydrogen that has a mass number of 2 actually is called deuterium. So anytime they talk about deuterium, that's just like heavy hydrogen. And there's a third isotopic form, tritium, which actually is unstable and is man-made. So that's why it's 0 abundance in nature. Boron, we saw the picture of a minute ago. Neon, we saw a figure of a minute ago. Okay, and magnesium. But actually, this adds one more column than we had before. This actually adds an important column that says, for that given isotopic form, how much does it weigh? Okay. All right. So before we got to this whole how much does an atom weigh, we talked about atomic number, which is number of protons, and we talked about mass number, which you look at the nucleus, you find protons and neutrons. And actually, in my notes, I say the protons and neutrons weigh about 1 AMU. So actually, you have an approximate mass. If you have the mass number, which is a whole number, you have an approximate mass of that particular isotopic form. All right. So, how do we calculate those decimal numbers, those average atomic weights? Well, we use a mathematical process, and so to kind of show that mathematical process, we're bringing in a Greek letter. This letter, this thing that looks like an E, that is a capital sigma. This is a sigma, and that means, in math, that means to add, or summation. Add, or summation. Anytime you see that. Of course, we don't just use it for here, but it's a process. So in this case, what we're going to add is for each isotope, let's see, how do I say this? Atomic weight of isotope. Do you remember that was the column I circled a minute ago? The weight of that particular isotope. And we've been talking about percent abundances of the isotopes, and I'll show you how to get from percent to fractional here in a minute. But what the summation means is that we take the first isotope, we take its weight and its fractional abundance, and we add, for the second isotope, we add the product or multiplying for the second one, its weight and its fractional abundance. And if there's a third one, we do that for the third one, and we do that for each different isotopic form. We just snag its how much it weighs and its fractional abundance. It's easy to show you. It's much easier to show you. So let's do an example. Before I do an example, I want to kind of say one more thing about fractional abundance. Because these sheets I passed around, they're abundances too, but it's not fractional, it's percent. Sure, you're like, well, what's the deal there? Well, to go from this percent, which is given on charts, to fractional, all you got to do is move a decimal. All you got to do is divide by 100. Okay, so when it said 99, thank you, 98% is this form of hydrogen, and deuterium is 0.02%. Okay? So that's the percent abundance. Okay? To get fractional abundance, and usually if I do a problem like this, I actually make columns. So to get fractional abundance, I'm going to move the decimal place 2 places. So that gives me 0.9998. Okay, what's that give me for this one? Yeah, 0.0002. Because if you take 0.02 and put it in your calculator, divide by 100, that's what you'll get. So anyway. All right, so now we're ready for an example. We're going to go back to copper. We said there were 2 isotopic forms of copper. we said that here's how abundant they are, and we said that here's how much they each one weigh. That works. So let's apply that process to coming up with, all we're doing, and this is one of the few problems in chemistry where you can actually check your answer. All we're doing, if you find copper, which is atomic number 29, all we're doing is trying to come up with that 63.55 AMUs. That's it with this information. That's totally it. So it looks like this. We're actually going to have two terms added together because we have two isotopic forms. So the first term is going to look like this. We're going to take the mass, which is 62.93 AMUs, and we're going to multiply it by the fractional abundance, which is the percent abundance, 69.09, divided by 100. So that's for the first isotopic form. And that's capital sigma, that means summation. So we're going to have to go back and snag that same information for the second isotopic form. And it looks like this. The mass is 64.928 AMUs. I got that from the previous, a couple slides ago. And its percent abundance was 0.91%. So I need the fractional abundance. So I go ahead and divide by 100. So you could either do it here or you could do it as another column. Now, for this sort of problem, and it will maybe even become more apparent, but you're going to round to, how do I say this? Round to 2 decimals if the element, I'll say if element heavier than boron. Okay, so the distinction there is if you find boron, I should say boron or heavier. So I want to say heavier than beryllium. I'll just put an E there. Okay, and actually the rules of rounding are a little bit tricky, I think, because you're multiplying and you're adding. So you have the both things going together. Adding is decimals and multiplying is sig figs. But bottom line, rounded to 2 significant figures, we should get the same number as this decimal number right here. It matches. Sometimes they don't match. Okay. So this is what we call a weighted average. In doing this, we're counting more, we're putting more stock in this one, this first one. This is more, it carries more than this one. It's a weighted average, that's it.
So which element do we round to?
So if it's a light one, so just the first, let's see, what is beryllium? Beryllium is the fourth element. So just hydrogen through beryllium, you're going to go with 3 decimals. I'll put that down here. H through Be, hydrogen through beryllium, you're going to go with 3 decimals. Other things from boron and heavier, you're going to go with 2 decimals less. Okay? Cool. All right. So do you guys have this slide? This is kind of an annoying. Do you have it all filled out though, hopefully? Good, because I was going to try to print this. I'm like, oh my gosh. Okay. So what you just did, we could kind of look at longhand, and this is what it looks like for copper. So the first the isotopic form, the copper 63 weighed 62.930 AMUs. There was, its relative abundance in 100 atoms was 69.09%. Okay, the copper atoms cancel there, and we're left with AMU per copper atom. Oh, sorry, the copper atoms of that isotope cancel, and we're left with AMUs per overall copper atoms. And then we do the same thing for the second isotopic form. And again, the units of for atoms of copper 65 cancel, and we're left with AMUs per copper atoms. So we multiply that out, and we get our 63.55 AMUs per 1 copper atom.
Do you want us to put it over one?
No.
We can just leave it as is.
Yeah, she asked, JC asked, do you need to put it over 1? And no, you don't have to. Very good. So I have a couple examples that just kind of show you why I run into a problem because students are like, averages, I know how to do an average. You're like, well, if I have 3 things, I add them together and divide by 3. And it just doesn't work that way because it's got to be what we call a weighted average. So if you did a simple average for the problem we just did, you'd come up with the decimal number for copper should be 64. And the reason it's 63.55 is because you have more of that lighter copper, okay? This is even a more extreme. So this is that hydrogen. We have much more regular hydrogen than we do deuterium, okay? So a simple average, if we were going to say, oh, if we got 50% of both, okay, we could just do a simple average, and the decimal number for hydrogen would be 1.5 AMUs. But the decimal number for hydrogen is 1.008 AMUs. It is way skewed towards the light version of hydrogen. Why? Because there's only a smidgen of deuterium. All right. So, yeah, I have a little spot sign. So this is one where you have to show your work. So, for instance, if I would give you that information about the 2 isotopes of copper, and like, what is the average atomic weight of copper? Well, it's 63.55. So you have to show your work. And I'm telling you on your Unit 1 and Unit 2 exam, which I think is going to be the 20th of next month. So your Unit 2 exam, I'm pretty sure, is going to be 10/20. I think we'll be in good shape there. 10/20, U2 exam. It will be fun. And you'll have one of these problems. So let's take a look at these right quick. Let's see, 95. Okay, so it looks like this. The first 2 problems aren't, to me, they're kind of like the other problem. I know there's a lot of words there, but all it is we're trying to go to that form where you put the symbol of the element, which in this case is C for carbon. The upper left-hand corner is your mass number, okay, and the lower left-hand corner is your atomic number, okay. So I think you should be fine. So determine the number of protons and neutrons in carbon-14. I think you'll be fine. This other one then is dealing with plutonium, mass number 239, and determine the number of protons and neutrons, and then write it in that form. And then this last one is like we just did in class. We're picking rubidium, and it has 2 isotopic forms. And this actually, when I work a problem like this on my answer key, this is how I do it. Because I hate the words things just drive me nuts. So I pull out the numbers into this format. And so we have 2 isotopic forms of rubidium. We have 85, mass number 85, mass number 87. My next column here is how much do each one of those atoms weigh. My third column is what is its abundance, and actually the circles there, red circles, are not because it's empty, but the red circles are you just need to pull the information down. It's all there. Bless you. And then I have a 4th column that basically converts percent abundance to fractional abundance by moving the decimal 2 places. So once I do that, I'm ready to go ahead and calculate it. So remember how that works. That's a summation for each isotopic form. You take how much it weighed times its fractional abundance, and you add them together. So you'll have 2 terms there. My last little bit of advice is don't forget, when you do this on a test or when you do it for your homework, don't forget that the periodic table is your friend in this case, where you can just check your answer. Okay? Any questions? Cool. Well, that's all I have today. Have a great weekend. It's Would that be PM or AM?